Now I promised in the last video that I was going to connect this to horizontal asymptotes. So a horizontal asymptote, if you remember from pre-cal, is this line horizontally that's involved in drawing graphs. But we never actually gave it a definition in pre-calculus. Here in calculus, we can give the horizontal asymptote a full definition. It is a horizontal line, y equals L, and it's called a horizontal asymptote if the limit as x approaches infinity of f of x is equal to L, or the limit as x approaches negative infinity of f of x is equal to L. So the horizontal asymptotes are actually defined as limits, as these limits as x approaches either positive or negative infinity. So as a remark, suppose we're sketching the graph of a rational function. We want to know what happens to the graph as x gets very large. For these large values of x, we know f of x will approach the asymptote L. But some of the asymptote knowledge that you have from pre-cal might be a little bit warped, a little bit skewed. So we're going to go through an example here. First off, we have y equals x plus 2 over x squared plus 1. What would be the horizontal asymptote? Well, we could go ahead and do our regular method. We would take the limit as x approaches infinity of x plus 2 over x squared plus 1. Using the quotient theorem, that would give us the limit x approaches infinity of x over x squared. We could, of course, simplify that down to the limit x approaches infinity of 1 over x, which would simply be 0. So therefore, we would have a horizontal asymptote at y is equal to 0. But what happens when you actually graph the function? Well, here we have a nice computer-generated graph, and we can go ahead and throw the asymptote on here. So we throw a dotted line. We can clearly see that the graph over here, as x approaches infinity, it approaches that asymptote. It's getting very close to that value. But what's happening over here at negative 2? It almost appears like the graph is crossing the asymptote. Well, let's go ahead and try. Let's plug in x equals to negative 2. So if we have our function y equals x plus 2 over x squared plus 1, if we plug in x equal to negative 2, we'll get y equals negative 2 plus 2 over negative 2 squared plus 1, which will be 0 over 5, which is just, well, 0. And so it looks like the graph has a value there. It looks like the graph equals the asymptote. Is that possible? Well, indeed it is. The graph crosses the asymptote. It definitely crosses. It passes through that line. And this is very, very important, that the graph crosses through the horizontal asymptote, because the horizontal asymptote is simply a limit. If you look back up here at the definition, it's just a limit. Sometimes you might have heard asymptotes referred to as magical lines that you can't cross, and that is an incorrect definition, and that is an incorrect assumption. There's nothing magical about an asymptote. It's simply a line that the graph will approach as the values get very, very large. Negative 2 is not a very large value, and so there's no reason the graph shouldn't approach or pass or cross the asymptote over here. It's only when x becomes very, very large, or if you were to go the other direction, very, very negative, that the asymptote will have any effect on the behavior of the graph. Now, let's go ahead and look at the limit x approaches infinity 1 over x times sine x, because I really want to help you understand this, help you grasp this point, because sometimes it's not always grasped in earlier courses in mathematics. Let's see if we can figure out this limit. Well, if we were to plug it in, 1 over infinity would give us a 0, but sine of infinity doesn't make any sense. So we're going to actually use the squeeze theorem here. We know that sine x is between 1 and negative 1. And we can go ahead and divide the whole inequality by x. Now, if you think about it, 1 over x times sine x, that's the same thing as sine x over x. But don't go thinking that this limit is going to be 1. That's only when x approaches 0. In this case, when x approaches infinity, we have to look at either side. So the limit x approaches infinity of negative 1 over x that's going to be 0. And the limit x approaches infinity of 1 over x is also 0. So we can say, therefore, by the squeeze theorem, the limit as x approaches infinity of 1 over x sine x is equal to 0. And so apparently we have a horizontal asymptote at y equals 0. Let's go ahead and take a look at what the graph looks like. So here we have the graph of 1 over x sine x. It's quite an interesting graph. It seems like it oscillates back and forth. But as you go further and further and further along the graph, it seems like those oscillations, they get smaller, they kind of die down. And you can see that as you go further and further and further along, the graph is indeed approaching the asymptote. It's approaching the value y equals 0. But the way it's approaching that value is very strange. It appears like it's crossing here at pi, and then crossing at 2 pi and 3 pi and 4 pi and so on. In fact, this graph will cross its asymptote infinitely many times. It will cross the graph forever. The graph and the asymptote, they are not repelled by each other. It's not some magical line that can't be crossed. In this case, it crosses over and over and over. It's always crossing. It's just that it's approaching that line. Now, this might seem very strange for you, but you could think of an analogy. I'll give you a picture to hopefully jar your memory. Think of those swinging doors in a Western movie when they walk into the saloon. As the person walks past the door, well, it swings open, and then behind them it swings closed. But it doesn't just stop there because the hinges are a little bit loose and it's been there for a long time. So the door, it swings back and forth and back and forth and back and forth as it settles down. If you were to visualize this on a graph, what's happening is the x-axis is the position of the door when it's perfectly closed and not moving. And when someone walks through, it's as though the door is now open. And then it closes and opens and closes and opens and closes. But now over time, there's some friction and some air resistance, and so the door, it oscillates less and less and less, and eventually, by the end, you could say the door eventually is fully closed again. And what that means in the mathematics is that the limit, as x approaches infinity, as you wait long enough, as you give it enough time, eventually the door approaches that position of being closed, but it crosses the closed position infinitely many times along the way. Of course it can cross the position. It's not a big deal in the real world for the door to cross that closed position. So you really don't want to think about asymptotes as these magical lines that you can't cross. It's not true and it's not helpful. So a quick multiple choice question here. Can you cross a horizontal asymptote? No, yes, maybe, or pi? Well, of course, the correct answer is yes. So one more question here, again related to the other one. Determine the limit as x approaches infinity of sine x. So go ahead and pause the video and give this a try. All right, so if we think about the graph of sine x, this one oscillates forever and ever, and it doesn't settle down. It doesn't approach a fixed value, which means that as x approaches infinity, well, sine x, it just continues to go between -1 and 1. So it doesn't have a limit in this case. It doesn't have an asymptote, which means that the limit does not exist. So now we're going to go ahead and look at some examples that might be a little bit more complicated. In particular, we're going to apply the quotient theorem, but we're also going to have an outside function. For these questions, you want to use the t substitution that we had learned earlier in the course, and I encourage you to pause the video before each example and give it a try. So for this one here, what we want to do is let t equal the x squared minus 5x plus 6 all over x squared plus 3x plus 4. Now by doing that, we can look at what happens to t as x approaches infinity. So we could say, well, we have the following. The limit x approaches infinity of x squared minus 5x plus 6 over x squared plus 3x plus 4 will be equal to, with the quotient theorem, the limit as x approaches infinity of x squared over x squared, which will just be equal to 1. And so this inside part is going to limit to 1. This means that as x approaches infinity, t is going to approach 1. So then we have the limit as t approaches 1 of ln t, which will just be equal to ln of 1, which we know is 0. Let's take a look at something like this. We have x cubed minus x over x squared plus 1. Again, we're going to go ahead and let t equal x cubed minus x over x squared plus 1. So we look at the limit as x approaches infinity of this quantity, x cubed minus x over x squared plus 1, which is going to be equal to, with the quotient theorem, the limit as x approaches infinity of just x cubed over x squared. Now we can see that the x squared cancels here, leaving me with just an x on top. So we're going to get infinity. As x approaches infinity, t also approaches infinity. For our limit, that means we have the limit t approaches infinity of ln t. Now you might argue, well, this is the same limit as before. Well, yes, it's still approaching infinity, but the inside has been simplified to just become a t. And you ask yourself, what happens to the graph of ln t as t goes to infinity? So if you think about the graph of ln t, or ln x, it looks like this. And so as you go really, really, really far out on the x-axis, the graph just keeps going up. It takes a while, but it eventually goes as high as you want. And so the answer will be positive infinity, based on the graph. Or in other words, ln of infinity equals infinity, but please don't ever write that. Now let's look at this question. Initially, it looks pretty overwhelming because we have so many things on the inside and we have a log. But if we do the t substitution, and I'll skip a few of the details here, we should end up with 4x squared times 5x on the top, and then 2x, and then times x squared on the bottom, of course based on the quotient theorem. And that's going to give us, well, 20x cubed over 2x cubed, which is just going to give us 10. So while skipping some steps, what we find is that as x approaches infinity, t, this whole thing being t, is going to approach the number 10. So we end up with the limit t approaches 10 of log base 10 of t. And log base 10 of 10 is simply 1. Again, by adding a log on the outside of the question, it adds a little more spice, a little more intrigue to the original limit question. It's the same idea of doing the quotient theorem, but now we have this extra step that at the end, instead of the answer just being 10, the answer is log base 10 of 10. So we get a final answer of 1. Now, there are some questions that get a little tricky for students. And the ones with arctan are some of the worst, because arctan is a function we haven't encountered a lot in our mathematical journeys. Arctan, which is another word for tan inverse of x, is the inverse function of tan. So if you can imagine your tan function and just drawing one copy of tan, we have something like this. The asymptotes are at pi over 2 and minus pi over 2. So tan inverse, where we swap x and y, turns those vertical asymptotes into horizontal asymptotes and turns that kind of S-curve into a S-curve that's side to side instead of up and down. So this is the graph of tan inverse of x. If you've never seen it before, well, there you go, now you've seen it. And so what does tan inverse have to do with limits? Well, if you ask yourself, as you go really far to the right on this graph, we approach the asymptote pi over 2. So the answer for this limit is pi over 2. And the justification for it is really just from the graph. From the graph. There's no algebra to do on this question. We just recognize that if we go to infinity for arctan, we get pi over 2. And if we go to negative infinity, the same thing applies. If we look at this portion of the graph, the answer should be negative pi over 2. Negative pi over 2. Now again, those are definitely worth learning and memorizing because the graph of arctan does come up now and again, and it's useful when we're solving these limit problems. So let's look at one again that has a little more going on with it. Here we have t equal to 3x minus 7x to the 4 over x cubed minus 2x squared plus x. So when we do the limit of that portion as x approaches infinity of 3x minus 7x to the 4, x cubed minus 2x squared plus x. With the quotient theorem, we should just get minus 7x to the 4 over x cubed. Now a bunch of those x's cancel, but we do still have an x left on top. And we have a negative, so we're going to get negative infinity. So that means that as x approaches negative infinity, as x approaches just infinity, t approaches negative infinity. So that means for our limit over here, we're going to get the limit as t approaches negative infinity of arctan of t. And based on the graph, this value is minus pi over 2. Again, remembering it from the graph. Let's try another one. Arctan of x plus 9x to the 5 over 9x to the 5, x to the 3, and minus 1. Again, omitting a few details, if we let this be our t, if we let t equal all that stuff, x plus 9x to the 5 over 9x to the 5 plus x cubed plus 1, we should see that as x goes to positive infinity, the quotient theorem allows us to drop everything except for the 9x to the 5 and the 9x to the 5. And 9x to the 5 over 9x to the 5 is just going to be 1. So as x approaches infinity, t approaches 1. Well, that's kind of strange. If we go back to our limit, we have the limit t approaches 1 of arctan of t. What is arctan of 1? Well, again, it's tan inverse. Tan inverse of 1, it's the opposite. It's asking yourself, what angle would you need on the unit circle? What angle on the unit circle would you need to get 1 from the tan value? And the answer would be at root 2 over 2, root 2 over 2, tan would equal 1. And that's going to happen when theta is pi over 4. So the answer here is pi over 4. If you want to do it in 2 steps, you could write it as simply arctan of 1, because you get to plug it in limit. And then arctan of 1 is pi over 4. All right, another weird arctan limit. Again, we need to figure out what happens on the inside. So I encourage you to pause the video, let the inside be t, and see what you get. All right, let's give it a whirl. We're going to let t equal the inside. And we're going to see what pops out. So we're going to look at the limit as x approaches infinity of 3x minus 1 squared, 2x plus 1 over x plus 1 to the 4. By the quotient theorem, we can drop almost everything. Just hanging on to that 3x squared, 2x, the x to the 4. It's going to give us the limit x approaches infinity of 9x squared times 2x over x to the 4. So most of those x's cancel, but we still have one x left on the bottom. So this is going to equal 0 because we have 18 over x, which approaches 0 as x approaches negative infinity or positive infinity. So this means that as x approaches infinity, t approaches 0. Hopping back to our limit, we have the limit t approaches 0 of arctan of t. Of arctan of t, which will just be arctan of 0. We get to plug it in. And again, what angle would give you tan of 0? The answer would just be 0 from the unit circle. All right, one last one to look at here. We have the limit as x approaches infinity of, there's an e going on. This seems tricky. Let's let t equal 3x squared minus 4x cubed over 7x squared minus 5. So we have the limit x approaches infinity of 3x squared minus 4x cubed over 7x squared minus 5. We use that quotient theorem to get the limit x approaches infinity of negative 4x cubed over 7x squared. Most of those x's cancel, but we're left with 1 on top. If you want to write one more step, we have the limit x approaches infinity of negative 4x over 7. That's going to give us negative infinity. So that means that as x approaches infinity, t approaches negative infinity. What is that going to mean? Well, back on our limit question, we now have the limit as t approaches negative infinity of e to the t. Now we need the e to the t graph somewhere, so let's throw that over here. E looks like this. And as you go really far to the left, if you think about that graph, if you go really far to the left, you're going to approach 0. And so from the graph, the answer here is 0. So hopefully that helped you with those limit questions. Make sure you give the worksheet and those textbook questions a try. I know limits can be tricky because there's a lot of different techniques and a lot of different tools, and it's hard to figure out sometimes which situation needs which tool and which technique. But I'd encourage you to just keep practicing, just keep trying. There are lots of other limit questions we'll get to when we want to practice for the upcoming midterm and for the exam. So if you're still having trouble choosing between each skill, don't worry about that too much. I'll have some mixed worksheets where you get to try all the limits in one big clump. But for right now, just make sure you try the worksheets, make sure you try the textbook questions, and as always, thanks for watching.